In this video, we will discuss phase transformations and the three groups they are categorized in. We will also explain the two stages of phase transformation, which are nucleation and the growth phase, and go over phase diagrams and their applicational use in problem solving.
The definition of phase transformation is a change in number and/or character of the phases that constitute the microstructure of an alloy. This occurs when there is a change in temperature or pressure. We will mostly go over solids and the cooling and deposition phase, where there is used to produce high-quality materials under a vacuum. The reason metallic materials can be used in so many varied ways is their range of mechanical properties they have. This range is accessed by a variety of means like strain hardening and grain size refinement.
Phase transformation is divided into three groups. The first group is diffusion dependent, where there is no change in the number of composition of phases present. Some examples include solidification of pure elemental metals, allotropic transformation, recrystallization, and grain growth. The characteristic grain structure in the pure metal casting shows randomly oriented grains of small size near the mold wall and large grains oriented toward the center. Another group is diffusion-dependent transformation, where there is some alteration in phase composition and often in the number of phases present. An example includes a eutectoid reaction. The third kind of transformation is diffusionless, wherein a metastable phase is produced. An example is rapid T-quenching to trap metastable phases. This video is an example of rapid quenching in an industrial process as a diffusionless transformation. Quenching is the rapid cooling of a workpiece in water, oil, or air to obtain certain material properties. A type of heat treating quenching prevents undesired low temperature processes, such as phase transformations, from occurring.
Nucleation is the beginning of a phase transformation process. This is the appearance of very small particles of nuclei of the new phase. There are two types of nucleation, and the distinction is made according to the location of the nucleation site. Homogeneous nuclei form uniformly around the parent phase, while heterogeneous nuclei form preferentially on pre-existing surfaces, container surfaces, or insoluble impurities.
Homogeneous nucleation involves Gibbs free energy as a driving force for the phase transformation. Transformation will occur spontaneously only when Gibbs free energy has a negative value. The main energy contributors to the total change in energy are the difference in Gibbs free energy when between solid and liquid, and the formation of a solid-liquid phase boundary. Gamma represents surface free energy.
Critical values R and G refer to two important values. R refers to the minimum radius for the embryo particle to be termed a nucleus. G refers to the critical or activation free energy, which is the minimum energy needed to form a stable nucleus. N represents the number of stable nuclei, and K1 is related to the total number of nuclei in the solid phase.
G sub V represents the volume free energy change and is the driving force for solidification transformation. G sub V is dependent on temperature, and substituting the formula into the critical value equations gives you the following equations. At the equilibrium solidification temperature, T sub M, which is the value of G sub V, is 0. H sub F represents the latent heat of diffusion, which is the amount of heat lost during the solidification process, and both temperatures are in Kelvin. Notice how all energies are temperature dependent.
This question is asking you for the critical radius of ice. In order to solve this equation, you must first use the formula for critical radius with the equation of the volume of free energy change substituted in. Now you plug in the values given to you in the problem. 25 times 10 to the negative third for gamma, 273 Kelvin for temperature, negative 3.1 times 10 to the 8th for the latent heat of fusion, and negative 40 plus 273 for the temperature. Now, after crunching your numbers, the final answer will come out to 1.1 times 10 to the negative 9th meters.
Another type of nucleation is heterogeneous nucleation, which occurs on surfaces and interfaces because it requires less energy. The activation energy for nucleation is lowered when nuclei form on pre-existing surfaces. Gamma represents three interfacial energies that exist at two phase boundaries. Gamma IL is the liquid surface, gamma SI is the solid surface, gamma SL is liquid solid, and theta represents wetting angle.
Using a similar process as for homogeneous nucleation, the values for critical radius and critical free energy can be calculated. The activation free energy values for both homogeneous and heterogeneous nucleation are proportional to each other and differ by the angle theta. By this formula, it can be seen that heterogeneous nucleation takes less energy than homogeneous nucleation.
After nucleation is finished, the growth phase begins, where we look at how the sphere beyond the critical radius grows. By examining below the equilibrium melting temperature, we can plot the rate of formation of nuclei in the liquid that may have a maximum rate of formation at the undercooling, which can be seen at the tip of the right side of the curve of the diagram. Once that phase is developed, it will continue to grow. Even though we are at a higher temperature and a high rate of diffusion, the distances over which the solute that has to be transported is very large. The growth rate diminishes as we get closer to the temperature.
As we have phase transformation, it doesn't occur all at once. It will take a while. We usually plot it on a graph like this. When we supercool the material, it will have a nucleation period at the bottom region, and some of it will begin to transform. And after a while, it will reach its peak, about midway. After a lot of it has been used up, all of it is transformed. And as Avrami-type kinetics, it follows this type of formula.
To solve this problem, we will use Avrami's equation and the transformation rate equation. We will first solve for the K value. After solving for K, we will obtain 3.57 times 10 to the negative 11. At 50% transformation, we will then use Avrami's equation again and solve for T by using the value we found. Remember that the transformation speed is at its peak at about 50% transformation. T equals 114.2 minutes. Then we can find the rate of reaction with Avrami's transformation rate equation. The rate of reaction is 8.76 times 10 to the negative 3 minutes to the power of negative 1.